Assalamu alaikum dear students. Today we will discuss in chemical thermodynamics the following topics, and that is spontaneous process, entropy and Gibbs free energy. First of all, we will start our first topic, that is spontaneous process. A spontaneous process is a process that occurs without any outside intervention, or it is a process that takes place on its own. Spontaneous process may be fast or slow. The faster one is the combustion processes. However, the conversion of graphite to diamond is a slow process. Moreover, you know that kinetics is concerned with the speed. However, the thermodynamics always concerned with the initial and final state of the system. So, spontaneous process is a process that takes place on its own, and it occurs without any outside intervention. This is an example of spontaneous process. This is the spontaneous expansion of a gas from a closed end to an open end. When we open this end, what happens? The gas moves from this end to the empty end and equally distributed in both the vessels. So this is the spontaneous expansion of a gas from one end to another end. Now, this is our another topic, entropy. We need to define. Entropy is denoted by a symbol S. Entropy is a measure of the randomness or disorderness of a system. Entropy is a deriving factor to derive second law of thermodynamics, as it deals with the entropy of the universe. Entropy is a thermodynamic function describing the number of arrangements that are available to the system. As we also know that the nature proceeds towards the states that have the highest possible probabilities of existing. So you need to know the various definitions of entropy, as well as these things, as they are very important in deriving various factors in thermodynamics. Now comes to second law of thermodynamics. It states that in any spontaneous process there is always an increase in the entropy of the universe. Moreover, the entropy of the universe is always increasing. For a given change to be spontaneous, entropy of the universe must be positive. Moreover, this is the mathematical form of second law of thermodynamics, that is change in entropy of the universe equals to change in entropy of the system plus change in entropy of the surrounding. Now this is the positional entropy of different states of matter. As you see in here, in solids the atoms are closely packed. However, in liquids the atoms are loosely packed, and in case of gases the atoms have wide spaces between them. So there is more disorderness in gas molecules, in gas atoms. So the entropy S gas is more than entropy of the liquid. However, the entropy of the disorderness in the solid atom is less. So the entropy of the solid is low as compared to the liquid, as compared to the gases. Entropy is also dependent on temperature, as the magnitude of entropy is always dependent on the temperature. The lower the temperature, the higher the impact to the surrounding, to the transfer of energy. Again, you need to remember this relationship, that is entropy of the universe is equals to the change in entropy of the system plus change in entropy of the surrounding. This is the mathematical form of the second law of thermodynamics. Entropy and exothermic process are also interrelatable. So you, in this case, you need to know the sign convention of entropy, change in entropy of the surrounding in case of exothermic process, and in case of endothermic process in which heat is absorbed, the change in entropy of the surrounding is negative. So what happens if the signs are positive and negative? In exothermic reaction, more disorderness in the surrounding. However, in endothermic process, less disorderness in the surrounding. So by changing the signs, the entropy, the disorderness in exothermic reactions are more as compared to the endothermic reaction. However, the entropy of the system must increase to obey the second law of thermodynamics. This is the mathematical form of entropy, that is change in entropy of the surrounding equals to minus delta H over T. You need to remember this mathematical form in order to solve some of the numerical problems, as delta H is the heat content or enthalpy of a system, T is the temperature, which is always in Kelvin. Why we are using the negative sign? Because we are talking about the entropy of the surrounding, that is always negative. Now this is the example for calculating the entropy of the surrounding. In the metallurgy of antimony, the pure metal is recovered via different reactions depending upon the composition of the ore. For example, iron is used to reduce antimony in the sulfide ore. These are the two reactions. The enthalpy for these two reactions are given. Moreover, we need to calculate the entropy of the surrounding for each reaction at 25 degrees Celsius and 1 atmosphere pressure. First of all, we deal with first reaction, and we need to calculate the entropy of surrounding. So for first reaction, what is enthalpy? That is minus 125 kilojoule. And what is temperature? 25 degrees Celsius. As the temperature is always in Kelvin, we need to convert this Celsius into Kelvin by adding up in 273, and the temperature in Kelvin comes out to be 298 Kelvin. Just putting the values in the main formula of entropy, we will get the answer, that is minus 419 joule per Kelvin. So this is the entropy of surrounding for the first reaction. Now move toward the second reaction. As in second reaction, the enthalpy of reaction is given, that is 778 kilojoule. Temperature is again 25 degrees Celsius. We need to convert this temperature into Kelvin by adding up in 273. Again putting the values in the same formula, then we can calculate the entropy of the surrounding, that is minus 2.61 kilojoule per Kelvin. Now comes to the free energy. This is also known as Gibbs free energy, as a physicist professor in the early 1800s worked very hard towards the modern thermodynamics. So this free energy G is also referred to as a Gibbs free energy. This is the mathematical form of Gibbs free energy, that is delta G equals to delta H minus T delta S. Typically this free energy is defined as the energy available to perform work. Gibbs free energy determines whether the process is spontaneous, non-spontaneous, or the process is at equilibrium. If delta G, the sign of delta G, Gibbs free energy, is negative, then the process is spontaneous. If the sign of Gibbs free energy is positive, then the process is non-spontaneous. If delta G equals to 0, then the process is at equilibrium. We will discuss this in detail in the preceding slides. Here delta G is 0. What if delta G is 0? What does it mean? If the value of delta G, Gibbs free energy, is 0, then the reaction is at equilibrium. What happens when delta G is less than 0? What does it mean? It means the Gibbs free energy is negative. The reaction is when the reaction is spontaneous in this case. When the Gibbs free energy is greater than 0, then the reaction is non-spontaneous. When it is at 0, what does it mean? It means the reaction is at equilibrium. So dependence on the temperature, Gibbs free energy also depend upon the temperature factor. As you see, Gibbs free energy equals to the heat content of the system, enthalpy, minus T is the temperature, and delta S is in the entropy. So in the formula of Gibbs free energy, we are dealing with the enthalpy, the heat content of a system, and we are dealing with the entropy of the system. Moreover, temperature is also a driving factor in deriving the free energy. So what happened? Spontaneity can change when the temperature changes. When the temperature increases or decreases, the sign of delta G must be changed over here. So it will derive whether the reaction is spontaneous or non-spontaneous. Temperature and spontaneity are not necessarily related. So what happened? A reaction with a negative entropy, a loss of randomness, would be less spontaneous at higher temperature. It does not want to happen, but it is pushed by the extra heat. So this factor, that is temperature directly affect the Gibbs free energy, but it did not affect the spontaneity or non-spontaneous of the reaction. Reaction rate. Free energy values tells us the reaction will occur. It predicts the occurrence of reaction. They do not tell how fast the reactions will. As I already told you that the thermodynamics has the limitation that it does not tell you about the kinetics of reaction. It only tells us about the initial and final state of the system. So it only predicts, Gibbs free energy only predicts the occurrence of reaction, whether the reaction is spontaneous or non-spontaneous. It only predicts that the spontaneity of the reaction or non-spontaneity of the reaction. It does not tell you about the kinetics of the reaction, that how fast the reaction is or how slow the reaction is. During a reaction, the reaction particles, as you know, during a reaction, the reactant particles must have effective collisions to form the product, as we already know this. So these factors are quite familiar to you. Delta H is the heat of enthalpy, delta S is the change in entropy, delta G is the Gibbs free energy, and this is the relationships of Gibbs free energy, that is delta G equals to delta H minus T delta S, as H is enthalpy and T is the Kelvin temperature. So these are the various sign conventions of delta H. T delta S is involved in this relationship, and delta G, and we have to predict whether the reaction is spontaneous. If the value of delta H is negative in this formula, and the value of T delta S is positive in the formula, then the value of delta G is negative. If the value of delta G is negative, then we know that the reaction is spontaneous. If the value of delta H is negative in this, if the value of delta H is positive in this formula, and the value of T delta S is negative in this formula, what happens? The value of delta G comes out to be positive. When the value of delta G is positive, then what happens? The reaction is non-spontaneous. In this case, you can also predict if both the signs of delta H and T delta S here are negative, then what happens? Again, the reaction is spontaneous if the absolute value of delta H is greater than the absolute value of T delta S at lower temperature. So these sign conventions can determine the value of delta G, that is either negative or positive. If the value of delta G is negative, then the reaction is spontaneous. If the value of delta G is positive, then the reaction is non-spontaneous. So this table tells you about the summary of prediction, that in which case the reaction is spontaneous and in which case the reaction is non-spontaneous. Now it is the example of Gibbs free energy. It is the reaction proceeding at 298 Kelvin, that is the decomposition of dinitrogen oxide to dinitrogen tetroxide. It is a gaseous phase reaction. For the reaction at 298 Kelvin, the value of delta H and delta S are given, that is 58.03 kilojoule and 176.6 joule per Kelvin respectively. Now, but we need to calculate the Gibbs free energy at 298 Kelvin. In this numerical problem, we need to calculate the Gibbs free energy. Simply apply the relationship of Gibbs free energy, as we know that Gibbs free energy equals to delta H minus T delta S. What is the value of delta H? It is given, that is 58.03. And what is the value of T? T is given 298 Kelvin. It is already in Kelvin, so no need to convert. What is the value of delta S? Delta S is 176.6. That is already given. Just putting all the values in this relationship, as we already know, and the answer comes out to be 5.40 kilojoule. As the sign of delta G is positive, so the reaction is non-spontaneous. It is not spontaneous at this temperature. Another example: iron metal can be produced by reducing iron 3 oxide with hydrogen. We are reducing iron 3 oxide with hydrogen, and iron metal is producing in this reaction. Heat of enthalpy delta H is given, while entropy, change in entropy is also given over here. We need to calculate A and B. Is this reaction spontaneous under standard state condition at 25 degrees Celsius? First of all, we need to predict whether the reaction is spontaneous at 25, and at what temperature will the reaction become spontaneous. We need to find the temperature in the second case. Now first of all, we need to solve A. To determine whether the reaction is spontaneous at 25 degrees Celsius, we need to determine the sign of delta G. Just apply this formula, delta G equals to delta H minus T delta S. At 25 degrees Celsius, as you know, when we convert in degrees Celsius, we just add up 25 in 273, and the answer is 298 Kelvin. Delta G for this reaction is delta G equals to delta H minus T delta S. As delta H for this numerical problem is given, that is 98.8. T is absolute temperature, that is 298, and we need to convert delta S into kilojoule per Kelvin. 0.1415 is in kilojoules. So just add up and subtract up, and putting all the values in this relationship, we get Gibbs free energy, that is 56.6 kilojoule. As you see, the sign of delta G is positive, so the reaction is not spontaneous. Now comes to part B. We need to find the temperature at which it becomes spontaneous. Just apply the formula of entropy. We can evaluate the value of temperature over here. T equals to delta H over S. Just apply this formula. As you know, the delta H is given, that is 98.8 kilojoule. However, the entropy of the system is also given, that is 0.1415 kilojoule per Kelvin. Kilojoule cancel out with kilojoule, and we have left with the 698 Kelvin after solving. So the temperature, the answer of temperature is 698 Kelvin. So at this temperature above 698 Kelvin, the T delta S terms become larger than delta H, making the Gibbs free energy negative, and the process is spontaneous. So at the temperature above 698 Kelvin, the process becomes spontaneous. Why is this positive term in this time? Because we are dealing with the system, not the surrounding. So as here 698 Kelvin is positive, it means that we are dealing with the system, not the surrounding. Entropy changes in a chemical reactions. Entropy also changes in the chemical reactions at constant temperature and pressures. Reactions involving gaseous molecules, the change in positional entropy is dominated by the relative number of molecules of gaseous reactants and products, as here 9 molecules are taking parts in the reactant side, or 10 molecules are taking part in the product side. So the change in entropy is increasing. Typically, more mole of a gas, more entropy. If the number of moles of a gas increasing, then there will be more disorderness in the system. So entropy changes in a chemical reaction, but it varies from reaction to reaction. I thank you for your attention. If you have any question, you may ask in your portal, or you can just email me at my official email address. I thank you all.